All right. Sorry we're a little late getting started, but at least we're going now. Any questions on anything we've done so far? Did everyone wind up getting a copy of the first test? Okay. Everybody got one. Okay. One person's already turned it in. There, you have until next week, but anyone who's ready to turn them in certainly can. Okay. Now, where we left off last time in Chapter 8, which is work and energy, we're in 8.1 still, which is work. Page 204, if you've got your text. Now, we're approaching this figure here. Now, this is going to introduce something that I'm not sure you've had the math on, but let me persuade you it's not that difficult. You may not have been used to seeing this, but the concept is not that hard. Like we said before, work is the product. Okay, let's go back a few slides. Well, not on here. Work is the product of the, for sure, all that we've covered it's in the book, but if you got it in the book, you see that earlier we said work is equal to force times displacement. Now, I put the dot in there. The book usually just writes it next to it. Now, what that means is work is equal to the force times the displacement in the direction of the force, or the displacement times the force in the direction of the displacement. They've got to be in the same direction. And most of the early problems, that's what we dealt with. But periodically, in fact, quite often, you'll have a situation where you're not just doing work on an object when you're pushing or pulling in the same direction that the object is moving. Like if I push on this chair here, I'm pushing downward, but the chair is moving that way. Now, if I push straight downward, it doesn't move at all because that's perpendicular to the motion. But if I push at an angle like that, it does move a little bit. Okay? This is my force. Now, remember, force is a vector quantity. Direction and magnitude are important. Now, a vector is made up of components. This vector of my force here has one component downward. That's just like this. That's not producing any motion at all. It's only the component that's in the direction of the displacement. That's the only part that does work. Okay? That's why it doesn't move very fast. If I push with the same amount this way, it moves quite a bit better. Same force, okay? But this way, actually I'm pushing with a greater force and just barely able to get it to move because only the force in the direction of the displacement is contributing to the work. Same thing with pulling. Okay, I'm pulling upward, but only the component in this direction is creating motion. This one here is not. Okay? You get name, please? Powell. Okay. Emily? Okay, got it. All right, so right now we're only missing Kayla. Good attendance tonight, folks. Way to go. Now, how we express that mathematically. Okay? The force, now this is showing a force upward, so I'll pull this way. Okay? The force is upward. There's a component of the force straight up, not doing any work, unless it lifted the chair off the floor, which it didn't. And I believe this must be Kayla, right? All right. Perfect attendance tonight, folks. Keep it up. Okay. And since a couple people have come in, has everyone gotten the first test? Anyone who did not get a copy of the first test? Good. Okay. We have to be able to express this mathematically. No longer will we just say it's the product of force times displacement. We have to say the force in the direction of the displacement. So how do we do that? Well, we do it using trigonometry. Now, don't get too fired up if you haven't had trig. Have any of you not had any trig whatsoever? All of you have had some trigonometry? No, not. Okay? Here is a very simple kind of way to deal with trigonometry. Okay? This is an angle we call theta. That's the most common name, just like x is the most common variable we use in linear stuff. Angle theta. Okay? Now, there's a horizontal component and a vertical component. This is actually the force here along the line there, the rope, the whatever that is pulling it. Now, as long as this is a right triangle, a perpendicular right triangle, which it is, then we relate the sides together. With this angle theta, we call this the opposite side, this the adjacent side, and this the hypotenuse. Hypotenuse on a right triangle is the long side of the triangle. Always the side opposite the right angle. Okay? The hypotenuse. Good Greek word, I believe. Now, here is the simple little formula that we have to relate these things. The sine of the angle theta is equal to the opposite side over the hypotenuse. The cosine of the angle theta is the adjacent side over the hypotenuse. And the tangent of the angle theta is equal to the opposite side over the adjacent side. Okay? Those are the rules. Those are true as long as you have a right triangle, which means you have a hypotenuse. These are the rules. Okay? Now, I roomed with a guy when I was in graduate school in Nebraska, and he was an undergraduate, and he used this phrase to remember it. Okay? Now, he said sa ka toa, and frankly, I can't tell the difference between sa and ka, but I've heard other people since then say so ka toa. So if you got that, you got it down. Sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. If that helps you remember, that's a good way to do it. Maybe first or second time I taught trig at what used to be Bessemer State Technical College, which is now the Bessemer campus of Austin State, I had a woman in the class, and she used this one. Some old hag caught another hag taking oats away. I don't particularly care for hags, but that's a pretty easy way to understand it. Maybe a year or two later, another woman in the class said she learned it with some old hen. Caught another hen. I like hens better than hags, so I go with some old hen. Caught another hen taking oats away. Any way you want to put it, this is how you relate these. Okay? So what does that have to do with anything? Well, the box is moving in this direction, so it's only the adjacent side, or the x component of that force, which is your hypotenuse, that is contributing to work. So find the trig function that relates adjacent and hypotenuse. There it is, cosine. So let's rewrite this as multiply both sides by h, and you have a is equal to cosine, or let's put that h in front, h times the cosine of theta, where H relates to the force. So this is the F sub x, that relates to the A, is equal to F, that relates to the H, times the cosine of the angle theta. Now, they either are going to give you the angle theta. Occasionally you might have to find that. That's usually not the problem at hand. Usually you have that. So this is the one we use in this formula. Not F anymore, but F times the cosine of theta. So this then becomes F times the cosine of theta times your displacement. Now, do all of you have some type of calculator, even if it's on your telephone? Okay? Sometimes with the telephone, when you hold it upright, it's a pretty simple calculator, and it may not have sine and cosine in it. Try tilting it to landscape mode, and then you'll see a lot more functions, including sine and cosine. Now, one little problem with it is, what are we measuring our angles? In this text, and in real life, most of the time we use degrees. So make sure you are in degree mode if you're dealing with degrees. I don't think this book uses radians at all, but if you are using radians, you need to be in radian mode. So make sure you got your calculator in the mode that's appropriate for the problem that you have. So this is the new angle we'll use. Now, our new formula they use, what they do, they relate the S and the F together just like they did before. So it becomes Fs times the cosine of the angle theta in between. This relates the adjacent, the x component to, it gets that out of the picture and uses the hypotenuse and the cosine of theta instead. So that's why we've got the new formula here. Work is equal to Fs times the cosine of the angle in between. That's when the force is not in the direction of motion. If you have the angle in between, that's what you use the cosine for. Okay. Now, you'll see in the book they use F sub x with bars around it. They will use F with bars around it. Now what that means is the magnitude, okay? The positive value, the absolute value of that force. So don't worry if one of these has a sign with it, like a minus sign, just use the positive value. I want to say that in just about all cases, and I believe that will be the case. Most of the time they will be positive, so you don't have to worry about the magnitude or the absolute value bars. So there's your formula. Let's do example 3. Let's see if the example 3 has a figure. I think this is it. A person pulls a sled along level ground at a distance of 15 meters by exerting a constant force of 215 newtons at an angle of 30.0 degrees with the ground, as shown in this figure, figure 8.7. How much work does she do? So what we need that they don't show here is she's going to pull this a distance of, and our symbol for distance is what? S. S is equal to 15.0 meters. All right. Now, as soon as you see that meters there and newtons here, what kind of units are we in? U.S. customary? No. SI units. You could call it metric, but the SI units, that's a better name for it. SI unit. The unit for distance in SI is meter, and the unit for force in SI is Newton. The angles are the same no matter what, so don't sweat the angle there. Now, the question is, how much work is she doing? So we're looking for work. What's the formula that relates force? This is your force. This is your displacement and work. especially when you have an angle involved. We just had it up there. Force times S times the cosine of the angle theta. That's it. So this is going to be 215. Now, rather than newtons, no, we'll write newtons, okay, times the S, that was your 15.0 meters, then times the cosine of the angle is 30.0 degrees. Okay. Now, depending on the type of calculator you have and whether it's your phone or not, okay, some calculators, when you press the cosine key, you'll see a parenthesis. You'll see it say COS and a parenthesis opens up. If it does, then you type in 30 after that, if you're in degree mode. Now, if you don't know what mode you're in, ask me and let me come look at your computer and we'll try to figure that out. Okay, you may know how to figure it out, so do it if you can. However, when you press the cosine key, it gives you something like an error or something else and tries to give you a number. That means you have to enter the number first, then the cosine. Press the cosine button. So, somebody try this and tell me what kind of answer you get. If you get something that says you have an error, then we'll investigate that. Or if you get a wacko answer, we'll investigate that. I want everybody to be able to enter this on whatever you have as a calculator. Now, if you don't have it with you tonight, please look on with someone and see how theirs work. Maybe yours will work the same way. Has anyone got an answer yet? 2,792.3. Okay. Say that again. 2,792.9. Okay, and the units will be Newton meters. Cosine theta has no units with it. The 30 has a unit of degrees, but the cosine is a dimensionless quantity. It's a ratio of two lengths, so it has no mention. Now, that's too many significant digits, because down here we have 1, 2, 3, here we have 1, 2, 3, here we have 1, 2, 3. Guess how many we need for our answer? 3. So you count 1, 2, 3 digits. Look to the right, that's a 2, less than 5, so you round that to a 0. So that would be 2,790 Newton meters. Okay? Does anyone recall what a Newton meter is? It has its own special unit. Joules, exactly. So this will be 2,790 joules. Newton meters are fine, but the singular unit is joule. Was there a question? I thought someone started to say something. Now, was anyone not able to get that answer?
I have a question.
Okay.
So if that was not a 2, if that was a
5,
it would be 280.
Okay, good question. If that had come over 2,795.9 Newton meters, it doesn't matter what the 0.9 is. I just put it because you use it here. Count 3 digits, 1, 2, 3. Look to the right, and that's a 5. That's 5 or more, so we round this up. Rounding that up makes 2,800. But you put a bar over that 0, meaning that's significant. Leave that one without a bar. And that would be joules then.
Why is it 4 digits and the answer you want to see?
Okay. Only 3 significant digits. See, these 3 are significant. That 0 is not. These 3 are because you put the bar over it. That one's not. But you have to have 4 digits because it's 2,000. You know, almost 3,000 joules. If you left off the 0, that'd be 279 joules. That's not nearly enough. You need that as a placeholder, but it's not significant. So that's why we threw away the 2, left it as 0. This one, we would have rounded up. That made that an 80 rather than 79. And then you put a 0 for this one, and this 0 that became, that one is significant, this one's not. So you put the bar over the significant 0. Now, if all 4 of those were significant, you could just put 1 bar here, leave that one off, because any digit between 2 significant digits would be significant. Okay.
And that 0 is simply significant because it's in the 3rd place.
The 3rd place, exactly. Yeah. You want 3 places of significance because you have 3 here, 3 here, and 3 here. If this would have been 15 meters without the point 0, you'd have 2 significant digits. If that had been 30 without the point 0, that would have been 2 significant digits. Okay? So you have to pay attention. All 3 of these were 3 significant digits, so you want the answer in 3 significant digits. That's the answer, not that one. That was a what-if situation. There was anyone not able to get the cosine to work? You weren't? Okay.
Do you have an iPhone?
What's that?
You have to do it first.
Yeah,
Put the number, and then press cosine,
cosine.
and then multiply the other 2 numbers.
Okay. So type in 215 times 15 times. Okay, now you type in 30 first, 30, and then press the cosine. Yeah. And then press equal. There you go. All right. Good deal. Okay. Anyone else have trouble getting this answer?
I did what you told me to do, but I got a different number.
Okay, let me see. All right, let me see you punch. See, we in the South are pretty violent. We punch our numbers in. Up north, they press the numbers. We punch. Okay, 215 times 15 times 30, and then press cosine equal. Wait, yeah, okay. I know what your problem is as soon as I saw that. Okay. I've got to find your mode key. See, when you did 30 and cosine, that gave you a very different number than what she got. And that's because you're in, wait a minute. Let's try it now. 30 cosine, yeah, that's it. And it says it's so backwards. And it said degree, you were in radian mode. When it says radian, you're in degree mode. Okay, so that gives you, you're in degree mode because you don't see where you're going. Okay. Anyone else not able to get the answer? Okay. Okay, you do 215 times 15 times, and you do the 30, and then press cosine, and then hit equal. There you go. Okay? Anyone else have trouble getting it? Okay. Now, if you are interested in something in the vertical direction, then you would use sine rather than cosine. But you're interested in this. And your formula is in cosine, so don't mess with it. It's right. Okay. Now, example 4. I don't think we have a figure for 4. So what I think I'll do is go to my other slide. I'm sorry, I've got to sneeze. Y'all awake yet? Okay. For people listening at home, they didn't know it was coming. All right. All right, let's go from current slide here. And here we have Juan and Sonia use a push mower to mow a lawn. Juan, who is taller, pushes at a constant force of 33.1 newtons on the handle at an angle of 55 degrees with the ground. So let me get my pen back. All right, here's the ground, and here's one pushing on his mower, okay, kicking out grass and stuff like that, and it's got the engine and all like this, and he's pushing at an angle of 55 degrees because he's taller. It's 55.0 degrees, okay? So here's one over here pushing, and he's pushing down with a force of 33.1 newtons, okay? So F is equal to 33.1 newtons, pushing downward. The book has them going in the opposite direction. I'm sorry, I'm going this way, okay? Sonia, who is shorter, pushes at a constant force of 23.2 newtons on the handle at 35 degrees. So here's Sonia's mower over here, okay? And she's pushing at an angle of 35.0 degrees. And she's pushing down with a force of 23.2 newtons. Okay, this is one, and this is Sonia. I haven't drawn them because my drawing is really ugly. Okay, as you can't tell. Okay, assume they each push the mower 3,000 meters. So we'll say this is 3,000 meters. Now notice there they put a bar over the middle zero. What does that mean? No, this one's significant. The 3 significant, this 0 is significant, and the one in between has to be significant. So that's 3 significant digits. That's how far one pushes, and that's also how far Sonia pushes. Same 3,000 meters. Okay, with a bar here. And that, by the way, is our displacement, our S, for both of them. Same displacement. Okay. Assume they each push. Who does more work and by how much? So we got to figure that out. Let's first do the work done by one. And what would be that? You tell me. What's the formula? F S times, say again? Cosine theta is what I heard? Cosine theta. That's theta for, this is force for 1, and the S is the same, and theta for 1. Okay? And Sonia does work for Sonia is equal to the force that Sonia pushes, which is different, times S, which is the same displacement, so we won't subscript that, times the cosine of her angle, and her angle is theta sub S. So let's plug in what we know. What was the force for 1? 33.1 newtons times, second? Okay, that's the theta. The S is the distance, 3,000 meters. Now, what's that? 55.0 degrees times the cosine of 55.0 degrees. Okay? You want to do that calculation first or write it out for Sonia? I don't care. Okay, you're going to do the calculation first? Someone tell me what you got. Second? 57,000. Boy, in the book I don't even see. Oh, there it is. 57,000. And what, any of those zeros significant? The first only, because 3 significant. And what units would that be? Joules, Newton meters or joules. Now that J is for joules, not for one. Okay? Let's do the same for Sonia. What's her force? 23.2 newtons. How far does she push? 3,000 meters, with the middle zero being significant. And her angle is 35.0 degrees. Punch her numbers in, you violent Southerners, and what do you get? You say that again? 0.012.9. Is that what you said?
Yes, sir.
Okay. To how many significant digits? 3. 1, 2, 3. Look to the right. 1. So we throw it away. I don't use it, so that'll be approximately 57,000 joules. Same amount. Within our significance, you can't tell any difference. Oh, and where do we put the bar? First zero. Perfect. So yeah, basically it did the same work. She didn't use as much force, but she had a lower angle, so more of her force was spent pushing. He was up at a higher angle, more of his force was pushing down, not in this way, so he was wasting some of his force, so to speak. And this past weekend I was doing a lot of mowing, and I didn't like wasting any more force than I had to. Okay. All right. You see in the book, flip the page, and you see they basically do the same amount of work, even though he exerts more energy because he's pushing into the ground. She's pushing in the ground some, but not as much as he is. So, ready for example 5? Yay or nay? Anyone need this up a little longer? Okay. Let me wipe that out. And example 5. Find the amount of work done in vertically lifting a steel beam with a mass of 750 kilograms at a uniform speed, a distance of 45 meters. Find the amount of work done in vertically lifting a steel beam. Now, I can't draw steel beams well, so I'm just going to give it a shot here. Okay. Something like that. You have a hidden thing here. Okay, there's a steel beam, and you're vertically lifting that, and this has a mass of 750 kilograms. Now, I don't see a bar there, so how many significant digits is that? 2. And you're going to lift it a distance of 45 meters. How many significant digits? 2. You're lifting in the same direction of the force. The force is up, the displacement's up, so you don't have an angle in here. Do we have a force? I don't see any forces here, do you? How do we get the force? What is the force involved? What are you having to lift if you're lifting a 750 kilogram beam? What are you lifting? Anyone know? The weight of that. Weight is a force. This is a mass, not a force. So we got to get the force, and what's the force due to weight? Wait a minute, that was the last chapter. We don't need to know that anymore, do we? Yes, we do. Physics builds on itself, just like math. So what is the force due to weight? Anyone remember that? Guess what? It has something to do with mass. Mass times the acceleration due to gravity. What's the symbol for acceleration due to gravity? G. Perfect. G. You got it right. Okay. The mass is 750 kilograms. And what's G in SI units? Because everything here is in SI units. Anyone remember? 9.80. What units? Meters per second squared. Okay. So that's going to be the weight, which is the force, and you're lifting it. So the work done is force times displacement. You don't have to worry about any angle because you're going in the same direction. So this is your S, is 45 meters. This is your force due to weight. That's that one. So what do you have? If you want to work that out, you can, or you can write them all down. 750 kilograms times 9.80 meters per second squared times 45 meters. No angle involved. What do we get? Pretty big number.
300,000.
Is that the number?
330,000.
Oh, 330,000. Okay. Let me go back and get that. Just 330,000 what?
750.
Okay. 330,750 what units? Say again? Joules. Excellent. Okay, looks like we might have a few too many significant digits there. How many do we need? 2. So we count 1, 2, look to the right. So 0. So put them all as 0. 330,000 joules. Okay? None of those zeros is significant. Okay? Let's see what we got. Now, they write it a couple of different ways. Our answer is perfectly fine, but because that's a pretty big number, they write it in scientific notation, which is move the decimal 1, 2, 3, 4, 5 places. So that would be 3.3 times 10, because each place represents 10, 10 to the 5th joules. That's one way to write it. You don't put any more zeros there because you only have 2 significant digits. Actually, if I were doing this, that just sort of takes up lots of room. I would have done this. Okay? Let's just go to the comma and make that 330. What's the next bigger unit after joules? If you move your decimal 3 places to the right or left, that becomes how many? What prefix? Means 1,000. Okay, if you walk, Kilo, exactly. So that would be kilojoules. Little k because that's just a unit. Capital J because it's named after John Prescott Joule. I like that better than writing 3.3 times 10 to the 5th joules. All those are correct answers. 330,000 joules, 330 kilojoules, or 3.3 times 10 to the 5th joules. All of them correct. They all get equal correct points. Okay? No sweat about how you... Now, if you're trying to get the same answer in the back of the book, you need to know how to do that. Okay? But it says, do you see that 330 kilojoules will also be an acceptable answer? Sure. I just said it would. Okay. No, I mean, that's not why. All right. So, problems 8.1. Now, there's a problem with 8.1. They left off 3 and 5. Okay, they're here. They just didn't put the numbers down. So, the 3 on the left there, under problems 8.5, 1, then the next one before the given should be a 3, and the next one before a given should be 5. Do any one of those 3, okay, 1 through 5, then any of the other odds, 7 through 13, and then perhaps any of the other odds, 15 through 23. So you got lots to choose from there. Now, do you have to do them all? No. You do as many as it takes for you to say, hey, I got this. Okay? Move on to something else. Okay? So you do enough so you feel comfortable, yes, I know how to work this. Now do them, some with angles and some without angles, and some lifting and some pushing and some pulling. You know, just do enough so you say, yeah, got it. Feel good about it. All right. Any questions on that? Let's go to the next topic, and that's power. Okay? I want you to think back, way back, first of the term, when we first started talking about how we describe motion. Okay? 2 entities are involved with motion. One is displacement, that's a distance, it could be in feet, meters, miles, yards, kilometers, whatever. The other was time. And when you combine the distance with the time, you got velocity. Velocity was the time rate of change of displacement, or speed was the time rate of change of distance. Okay? So what you do, get everything, measure the displacement or the distance, and then say, well, let's divide that by time, and that gives us new time. Now, once you got velocity, divide that by time, and you got what? Acceleration. Okay. Well, we've just been dealing with work. Well, now that we got work down, let's divide that by time, and that gives you power. Power is the rate at which you do work. Okay? The rate at which you do work. The time rate at which you do work. Okay? And that's exactly how they define it here. Power is the rate of doing work. I'm going to put time rate. That's usually what we understand the way of doing work. Oops. Okay? Writing that mathematically would be power, P stands for power, is equal to W standing for work, capital W, standing for work per unit time. Time rate of doing work. Work divided by time. Now, what units do we use here? What's our unit for work in the SI unit? Oh. Come on back. Yeah, there we go. Okay. There's something about this when I twist it the wrong way, it flicks up. Okay, what's the unit for work? You just gave it to me several times. Unit for work is the answer to most of our last few problems. How much work was done? What answer did you give me? Say again? Newtons was force. Joules, okay. This is a joule per, and what's the typical unit for time? Second. So a joule per second. Now that has a special name. And that special name is watt. Okay? Named after a Scottish engineer, physicist named James Watt. Okay? Now, the symbol for it, of course, is capital W because it's named after him. Don't get this capital W confused with this one. This is a parameter standing for work. This is a unit standing for watts. Units always have numbers in front of them. Parameters usually don't. So this would be 15 watts, 250 watts, something like that. Okay? Now, does watt sound like a unit you use any other time? Say again? Any of you ever look at your power bills? They're measured in what? Okay, actually it's usually in kilowatt hours, but that's the same watt that we electricity, quite often you measure it in kilowatts, okay, or watts. Okay, that's energy you're talking about. If you're talking, power, you're talking about. If you're talking about watts, you're talking about power. Okay, so that's the unit for a joule per second is a watt. Okay, and what would a kilowatt be? Kilo means 1,000. That would be 1,000 watts. What do you think a megawatt would be? Second? 3 more zeros after 1,000 would be? I don't have those. No, 3 zeros. What do you say? Million! Mega means million. Okay, and since we've already used little m for milli, we use little mu for micro. What are we going to use for mega? Because it's a big unit, we use capital M. Even though it's not named after anyone, and all the bigger units after that are always capitalized. Now, if you're dealing with computers and you talk about memory or you talk about how fast something does, like the frequency, you use quite often kilobytes or hertz, or you use megabytes if it's millions of them, or megahertz if it's 1,000,000 cycles per second. What's the next biggest one? Some of your computers are now measured in gigahertz, capital G. That would be billions, okay? And gigahertz would be capital G hertz, HZ. And then after that, I think they get into tera. And you do see that occasionally nowadays. We've gotten really, really big. Okay. Now, they named the unit of power after James Watt because he first defined power, but that was before the SI system was there. Or he was Scottish, so he used the British system, which we call U.S. customary now. What would be the units for power in the U.S. customary? What's your unit for work in U.S. customary? Work is force times displacement. Force in U.S. customary would be, remember, weight is a form of pounds, okay? That would be a pound, that's the force. And what would be the distance in U.S. customary? Foot. So this would be foot pounds, okay, per second, okay? Now that doesn't have a special name, but James Watt gave an equivalent something to it because he was looking, this was way back in the days, in fact it was shortly before the steam engine came into being, because James Watt helped develop the steam engine. But before steam engines were there, they used horses. Now, what kind of power unit would you use with horses? Horsepower. And here's how James Watt, he's the one who came up with this, he defined it as the amount of work that a standard dray horse, that would be those big old Clydesdales or something like that, would do in a day. And that horsepower, so 1 horsepower, HP, that doesn't stand for Hewlett-Packard, is 550 foot-pounds per second. Or, I don't ever use this one, 33,000 foot-pounds per minute. You just multiply this one by 60 and you get that. Okay? Now, if you wanted to do how many it would be in a day, multiply that by another 60, you get foot-pounds per hour, and then multiply that by, say, 8 hours, which would be a standard work day, maybe 10 hours back then, I don't know what. And you get how much work a standard dray horse would do in a day. We don't need to know that. 550 foot-pounds per second is enough. That's 1 horsepower. Okay? That's a conversion you should know. Okay. So he named the horsepower. Later they named the power in the metric system, the SI system, after watt. So that's why it's capital W, watt. Human horsepower. Okay? How much equivalent horsepower do you possess? What you can do is figure out how many foot-pounds you can lift or carry or do something else, divide that by the time, and then divide it by 550, and that would be what your horsepower was. You might be able to do more than 1 horsepower, possibly, or pretty close to 1, for a short period of time, but if you do it over an entire day, you're going to be considerably less than 1 horsepower. Okay. Let me go on and give you this dumb example. Okay? I told you all about digging out our patio, right? Okay. I worked at that for about 5 weeks, pretty solid. Okay? We may have had a few rainy days, or I may have had a few days to do something else, but I worked at that for about 5 weeks, digging out the patio. And the end of those 5 weeks was about the time Labor Day was getting there. And right after Labor Day, we were supposed to start back teaching. I knew once I started back teaching, because I had the last half of the summer off, that's why I knew it was 5 weeks, because I wasn't teaching any classes then. But once I was going to start back teaching, I was going to have nothing but weekends. Well, because that big boulder in the middle of it and all the problems I had, I only got about half of the patio done. It was more than half area-wise, but it was getting deeper and deeper soil. So I only got about half of the soil moved in those 5 weeks. And I worked at it pretty steadily. Pick, shovel, and wheelbarrow, except for that rock. Okay? Well, we had to do something. Now, one reason I had not hired anyone to come do it, there was no place to work. Our house was right here. Trees were right here. There was just no area to work. We had just no place to work. But by the time I had about half the patio dug, then you could get a bobcat in there, and you could work on the surface that I had cleared. So we decided to go on and call for a bobcat, a guy who did work on a bobcat, and he brought that in. I think it was on Labor Day. I'm not sure. It may have been the Saturday before. Okay, I had worked for 5 weeks and moved about half of that soil. He came in with his bobcat, and in about half a day or maybe 3/4 of a day, he dug the rest of it. What was the difference between me and the bobcat? We both did about the same amount of work. I shoveled out half of the soil, he shoveled out half of it. But what was the difference? The time. It took me 5 weeks, it took him half a day. Okay? Guess what? That bobcat, I'm just going to make a guess here, was probably on the order of, it was a big old bobcat. I would say 200 to 300 horsepower. Me, considerably less than half a horsepower. So you see, he was able to move a lot more, do the same work, but in a lot less time. Because power is work divided by time. If we did the same work, but I took more time, he had more horsepower. Right? Okay. Dumb story over. Let's do the freight elevator. A freight elevator with an operator weighs 5,000 newtons. Weighs, what's that a measure of? What does newtons measure? Force. So that's the force due to weight is 5,000 newtons. And do one of those zeros have something over it? The middle one has a bar over it. What does that mean? 3 significant digits. That 0 is significant, the 5 is significant, the one in between has to be significant. The one at the end is not. But you need it there because it's 5,000, not 500. Okay? A freight elevator with the operator weighs 5,000 newtons. That's the force due to weight. If it is raised to a height of 15 meters, so the S, this is the, I would like to use H, but they use S. S is 15.0 meters. That's how high it goes. Okay? And it's lifted straight up. That's in the direction of the displacement. Okay? How much power? Oh, in 10 seconds. So your T here is 10.0 seconds. Okay? How much power is developed? What is power? We just had it. What is power? Work per unit time. Okay? And what is work? We've been doing it. What is work? Back in 8.1, what was work? Formula for work? Oh, how soon we forget. Force times displacement. And that's work, and we're dividing by time to get power. Do we have our force? This force is the force due to weight. So this would be 5,000 newtons with the middle zero significant times, what's the displacement? 15.0 meters divided by 10.0 seconds. Okay? Now I'm going to make this a little easier. I'm going to divide that 10 into one of those zeros, just to make it easier. It's 500 times 15. I think I can almost do that in my head. 7,500, isn't it? What's that? Because I divided out a 0. If you don't want to divide out a 0, do 5,000 times 15 divided by 10. See if you get the same answer.
Oh, okay.
Yeah. See what? Okay. Okay. Is that really 7,500? I think it is. Yeah. Okay. Now, do any of those, either of those zeros have a bar over it? The what? The first one, you're absolutely right. 3 significant digits. And what would that unit be? Okay, you could say Newton meter per second, or you could say joules per second, or you could say what? What? Yeah, okay, yeah, watt. All right, watts. 7,500 watts. Or, if you didn't want to have such a big number there, we could move the decimal how many places? 3 places. That stands for 1,000. That would be 7.50. We got to have all our significant digits there. What unit? What means 1,000? Kilowatts. Perfect. That'd be 7.50 kilowatts. You don't have to do that, but it's just another way, a little bit shorter number to write, and then just put a prefix of K in front of it. Okay? They left it as 7,500 Newton meter per second, which I don't know why they didn't go on to change either joule per second or watts, but any one of those would do, or change it to 7.50 kilowatts. All of those are correct answers, by the way. Okay? That was example 1 in 8.2. Ready for example 2? Everybody? Any questions before I delete this? Okay. Deleted it is. The power expended in lifting an 825-pound girder. So 825 pounds. What does pounds measure? Force. That's force due to weight. That's a force. To the top of a building 100 feet high. So that's going to be, and that second zero is significant, that is what? What's the parameter that feet measures? It's how high you lifted it. What parameter is that? We've been using it all night. Displacement. What symbol do we use? S. That's your height, your displacement. I would use H, but they use S. Okay? Is, and then this is from the very first, the power is, so P is equal to 10.0 horsepower. Uh-oh, Houston, we have a problem. Oh, the question is, how much time is required to raise the girder? So time is the unknown here. Okay. We've got a problem here because the force or weight is measured in pounds. That's good. The distance or displacement is measured in feet. That's good. But the power is measured in horsepower. What is a horsepower? If we're wanting to make a conversion here, what are our standard units for the U.S. customary system for power? Foot-pounds per second. Right. So we're trying to get from horsepower to foot-pounds per second. Now, notice I put two blanks here. The first blank is for numbers, the second blank's for units, but what do we put in its place first? Always put the units in their place. So one of these units go in the numerator and one in the denominator. Horsepower is one unit, foot-pounds per second in the other. Which goes where? Always put the units in their place. Make a guess. Anybody? Somebody help me, I'm dying up here. What unit goes where? One goes in the numerator, one in the denominator. You. Say again? Where does it go? Absolutely. Horsepower in the denominator and foot-pounds per second in the numerator. Why? So the horsepowers can cancel out. And you're left with foot-pounds per second right where you want them. Okay? Very good. Now we have to put the numbers in the place. How many foot-pounds per second is 1 horsepower, or how many horsepowers is a foot-pound per second? Uh-oh, that was a couple. Say again? 550 which? Foot-pounds per second. 550 foot-pounds per second is 1 horsepower. Now we have our conversion in place. So when we multiply that by 10, that gives us, I can do that, that would be 5,500 foot-pounds per second. Now, since that zero is significant, that means this one is significant here. Not the last one, just that one. Now I think we can calculate, we still got some work to do. Tell me what the formula is that relates power, force, displacement, and time. What formula relates those? One we've been using. Help me, somebody. What's the formula that relates power, force, displacement, and time? Say again? Okay, work is what? Force times displacement. Yeah, that's involved. Power is what? Work per unit time. Got it. So the work is force due to weight times displacement over time. All right. Now that relates everything we've got here together, but we're looking for time. Okay? Now, there's one of two ways we can do this. We can either plug in the numbers and then manipulate, or we can manipulate the letters and then plug in the numbers. I call it plug and chug or chug and plug. It doesn't matter which way you do it. Which way you want to do. Plug in numbers first, then manipulate, or manipulate the letters first and then plug in the numbers. Up to you. Manipulate what? The letters. And then plug in the numbers? Okay. So we're looking for time. That's what we're looking for. So we need to get it out of the denominator and into the numerator. So what would we do? Multiply time on both sides of the equation. Okay? We're sort of ignoring this in here. Well, the time has disappeared here, but it's over here now. We're trying to get time by itself, so what do? Trying to isolate the time. Divide by the power. Very good. Okay. So what we have now is time is equal to force due to weight times displacement divided by power. So now plug in the numbers. What's our force due to weight? 825 pounds times, what's our displacement? 100 feet divided by, what was our power in foot-pounds per second? 5,500, with the first zero being significant, foot-pounds per second. Notice the units. They're your friends. Don't lose them. The feet cancel out. The pounds cancel out. You're left with 1 over second, which means 1 over second. Think of that as a division. 1 divided by 1 over second. How do you divide a fractional form? And yeah, so that'd be 1 times second over 1, so this will be in seconds. There's a great unit for time, isn't it? So our answer will be in time. So, now here, again, I'm going to be lazy about this. I'm going to wipe out these 2 zeros and those 2 zeros. So now all I have to do is do 825 divided by 55. I could divide it by 5s too, but that would be too hard. 15. Okay. You think that's enough digits? No, we had 3 here, 3 here, 3 here. I think we need a 0.0 there, don't we? Still 15, but we need to show we got 3 significant digits, 15.0 seconds. Does that seem reasonable? Yeah, that seems pretty reasonable. Lifting at 100 feet, 825 pounds? Huh, I can't do it in 15 seconds, but yeah. Let's see how the book did. 15.0 seconds. Good for them. All right. Good deal. Any questions? All right. Ready for example 3? What's that? Have you got questions before I erase this? Oh, we just need to move on though, don't we? Okay. All right. Be sure you ask questions if you got them. Okay? You can always ask later too, but while they're fresh, that's a good time to ask. Example 3. The mass of a large steel wrecking ball is 2,000 kilograms. The mass is 2,000 And what, is there a symbol somewhere there? Bar over the middle zero, kilograms. That's mass. That's not weight. That's not force. That's mass. What power, so we're looking for power, there's our unknown, is used to raise it to a height of 40.0 meters. So 40.0 meters. What's that symbol? Our distance or displacement. What do we use for that? Or the book uses anyway. S. That's your height or your displacement. S. Okay? Is done if the work is done in 20 seconds. What's 20 seconds a measure of? That's your time. Okay? We got all of the information down here except something. Yeah, we're not got a force here. How can we get a force out of that problem? Second? Ha! You got it. The force due to weight is, what do you say? Mass times acceleration due to gravity. You got it. So this is going to be, the mass is 2,000 kilograms. That, by the way, is 2 metric tons. Okay? That's a big wrecking ball. Okay? Times what's G in the SI units? 9.80. What units? Meters per second squared. And if you multiply those out, I'm pretty sure you get 19.6 or 19.6 0 0 19,600. Does that sound right? Yeah. Because this is almost 10 times 2,000 would be 20,000. This is just under 20,000. What units would that be? Kilogram meter per second squared. Newtons. Excellent. Okay. So there's our force. So we're looking for power. What is power? What's the formula for it? Did you say force times displacement? That's your work divided by time. You got it. And what do you put in here? This is force due to weight. What's that? Force due to weight. We just did it. Didn't we? 19,600 newtons times your displacement of 40.0 meters divided by 20.0 seconds. And again, I'm going to be really lazy about this and divide my 20 into 40 and get 2, because 20 goes into 40 2 times. That could be 2.00, but I'm not going to worry about that right now. So all I have to do is multiply that by 2, and that gives me 9, 2, 0, 0. 39,200 what units? What? What? Yeah, okay. Okay, now that's an awfully big number. What if I want to make it a smaller number but a bigger unit? What would that be? 39.2 kilowatts. Very good. Let's see how the book did. Oh my goodness, look at that. They got it right. Good for them. 39,200 watts or 39.2 kilowatts. Make sense? Good deal. All right. Ready for example 4? Yeah. Any questions before I move on? Everybody see what we did, how we did it. Now, you don't have to take the shortcuts I do. You can multiply the things out. Calculators help. I don't have a calculator, so I'm doing it in my head. Just makes it easier to do because my head hurts when I work too hard. All right, so I'm going to erase that, and we'll move to example 4, top of page 211. A machine is designed to perform a given amount of work in a given amount of time. Ooh, no numbers in this one, are they? A second machine does the same amount of work in half the time. Find the power of the second machine compared to the first machine. Anyone want to make a guess? How much? Remember me and the Bobcat? Now, it's not that extreme, but it's something like that. The first machine, me, okay, designed to perform a given amount of work in a given amount of time. The second machine does the same amount of work, but in half the time. What's the power of the second machine compared to the first? Second? Doubled, exactly. Twice the power. You're absolutely right. Okay? That sort of makes sense. Here's how they do it. It's, and it's, to me, just about easier to just think through than to actually do, but let's do it. A machine is designed to do a given amount of work in a given amount of time. So let's call W the amount of work. That's from machine 1, okay? And T is the amount of time by machine 1, okay? So the power then would be work divided by time, right? Now, for the second machine, same amount of work, okay, machine 2, but the time for machine 2 is 1/2 the time for machine 1, right? Isn't that what it said? The second machine does the same amount of work in half the time, so half the time of machine 1. So its power, the power for machine 2, would be same work divided by T over 2. Well, how did we say we divided fractions? That would be W divided by T over 2, which would be W times if you're dividing a fractional form, you multiply by the reciprocal, 2 over T. So what does that give you? 2 times W over T. Well, W over T was the power of the first machine. Power of the second machine is twice the power of the first machine. I don't know what that other line is there. Okay, and that's exactly what you thought through. Twice the power if you spent half the time. Oh, that was so easy. We do another one, can't we? Is there a question, or is that a stretch? Okay. Okay. Any other questions or stretches? Okay. Whoops, wrong button. Okay. So I'll erase that one. That was sort of da-da. Okay. Let's move to example 5. See, we go to 6:30, right? Yes, okay. I want to make sure I wasn't running out of time. Okay. Example 5. A motor is capable of developing 10 kilowatts of power. So the power here is 10.0 kilowatts. How large a mass can it lift 75 meters in 20 seconds? Okay, I have a feeling we're not going to want it in kilowatts. We may want it in watts. So how many watts is 10 kilowatts? 10,000. You're absolutely right. K means 1,000. That's 10,000 watts. Okay? Now, this first number has 3 significant digits. To make this meaningful, that means the bar goes over the second zero. Okay, the second zero. So you have 3 significant digits there. Okay. So there is the power. How large a mass, so we're looking for mass here, that's the unknown. Can it lift 75 meters, 75.0 meters? What would that be a measure of? Displacement, S, okay, in 20.0 seconds. What's that a measure of? Time. Okay. What are we missing here? Force. What is our force going to be? Oh, yeah. Force is going to be, we just did it a little bit ago, is force due to weight is okay. Have a feeling she's looking for the EMT class, I hope. Or she was looking for the dummy that we don't have back there anymore. Okay, whoever. Okay. What do we do? What is force due to weight in terms of mass? We've done it before. Is what? Just did it a couple problems ago. Say again? You may have said it. I can't hear well. Is what? I hear someone talking, but I can't make it out. Sorry, my hearing's terrible. Mass times acceleration due to gravity, mg. That's going to be our force, and that's where the mass will come into play. So, what we might have to do is figure out, let's solve this for mass, and that means you would do what? I don't think so. We'll figure that out later. Yes. Yeah, we haven't gotten it yet, but when we do need it. Say again?
This equation is about finding the mass.
That's what we're looking for. We're looking for mass because it says how large a mass. So if we can figure out what the force is, then we can go back and figure out what the mass is from this equation. So what is our formula that relates power, force, displacement, and time? Anybody? I think someone may have mumbled it. What is it? Almost that. Okay. What is our formula? Power is equal to force times displacement divided by time. That's it. Okay? Now, we don't know the force. Okay? But we do know that's mg. So let me write that down instead. mg times displacement divided by time. Okay? Now, that's our formula now. We want to know the mass. We know all the rest of them. I haven't written down what g is, but I think you know what that is. So how can we solve this for mass? Let's do it one bite at a time. How do you eat a 5,000-pound elephant? One bite at a time. Okay? So here's how we do it. Okay? Let's do first. Let's get rid of the t. How do we get rid of the t? Multiply by t. But multiply both sides of the equation. All right, that's out of there. We want mass by itself, so what do we need to do? We want to get rid of G and S. How do we do that? Hint, they're all multiplied together, so how do we get rid of them? Divide by G and divide by S. So divide by G and divide by S. The G's are gone, the S's are gone. So that leaves us with mass is equal to power times time divided by G times displacement. Let's plug and chug and see what we get. What's our power? Say again? What?
Can you start back over when you got
Okay, where?
I lost you at the time.
When I did finding the time?
Like, after you did the time, I lost you.
Okay, all right. Let's back up. Y'all gave me the formula. P is equal to force times displacement divided by time, right? With me there. And then from here, we know the force is mass times acceleration due to gravity. That's times the displacement divided by time, right? Now, what do we know and what are we looking for? We're looking for mass. We know power. That's given here. We know acceleration due to gravity. We haven't written it down, but we know that. We know displacement. Is that okay? Come on back. All right. Where did you go? What did you do? Okay, let me see if this does anything. Just seems like, I mean, I can see a light up there, but nothing's coming on the screen. Ah, there it's coming. Is that it? Yeah. Okay. We knew power. We knew mass. We're looking for mass. We know acceleration due to gravity. We haven't written it down, but you know what it is, right? Please say yes. You know what G is? Yeah, we know it. Yeah, okay. And we know what the time is. There it is. And we know what the displacement is. I mean, there's the time, there's the displacement. So we know them all except mass. So let's isolate the mass. Get it by itself, right? Are you with me? Okay. We want to isolate the mass. So we want to get all the rest of the things away from it. We want a naked mass there. We don't want anything else with it, okay? So let's first get rid of the time by multiplying both sides by time, right? So that gets rid of time. Agreed? Okay. We still got G and S with the mass. So let's get rid of them by dividing by G and dividing by S, S being the displacement. So over here we're going to divide by G and divide by S. Well, here the G's go out and there the S's go out. So now we got mass by itself, and that's equal to power times time divided by acceleration due to gravity times displacement.
And that's how you got the bottom.
That's how I got it at the bottom, yeah. Okay? Now let's plug. We did our chugging, let's do our plugging. What is our power? Up there at the top. 10,000 watts. What? Watts. Okay. Times, what's our time? 20 seconds. 20.0 seconds. Okay. Divided by, oh, and by the way, what is a watt? Let's get the basic units for a watt. Okay. Let's look at this right here. Remember where we started? This right here? It's this. Force is Newton meter per second. A force is a Newton, S is in meters, and your time is in seconds. So power A watt is a Newton meter per second. Well, let's break down what a Newton is. A Newton is, and we got that from here right here, that's a kilogram meter squared, meter per second squared. That's mass times this. That's what a Newton. Times another meter divided by time. Another second. Okay? Okay, I've got my unit sort of screwy here. Okay, so what do we have here? But we have kilogram meter squared per second squared divided by second. So that's really per second cubed. We're going to get rid of that in a little bit. Okay? That's what we've got here. A watt is a kilogram meter squared per second cubed. So that's what we're going to put here. Kilogram meter squared per second cubed. Okay? Well, when we multiply this by second, we're going to go back to being a second squared. Okay? Now, we're dividing by g, and what was g, by the way? Second? A little louder? Okay, the acceleration due to gravity, but what's its value? 9.80. What units? Meters per second squared. Great acceleration unit. And what's our S? 75 what? 0.0 what? Meters. Okay. Now let's look at what we got. Here's a meter squared up here. Here's a meter times a meter down here. That makes a meter squared. Here's a per second squared here because we divided out one of the second. There's a per second squared there. What's the only unit we got left up here? Kilogram, which is a great unit for mass. Okay? So if you punch the numbers in, and then we'll see what we got. The unit should be kilogram. Now what units, what number do we get? 10,000 by 20 would be 200,000. Divide first by 9.8 and then divide it by 75 and see what you get. 20,000, first divide it by 9.8 and then divide that answer by 75 and see what you get. Anybody? 272, is that what you said? 272 kilograms. I think she's just reading out of the book, aren't you? No, good deal. All right, excellent. 272 kilograms. Perfect. That's what the book got to. All right. Ready for any questions on this? Does that make sense? Okay. Any questions? All right. Let's move on to example 6, the last example in this section, 8.2. So let's hit example 6. A pump is needed to lift 1,500 liters of water per minute. Ooh. 1,500, and there's a bar over the first 0, liters of water per minute. Okay? I don't know what that is exactly. It's volume per unit time. I don't know. Just some sort of rate. A distance of, I know what distance is. What symbol do we use for distance? S. S is 45.0 meters. Okay? What power, so we're looking for power, and they want it in kilowatts, but let's calculate it in watts first. Must the pump be able to deliver? So this is the unknown, the power. Now here they give you a hint. 1 liter of water has a mass, and 3 bars like that don't mean equal, but it is equivalent to 1 kilogram. Because liters and kilograms measure different things, but they're equivalent. 1 liter of water has a mass of 1 kilogram. 1 kilogram has a mass of 1 liter. Do any of you, your cup there, do you know what size that is? Well, let's just say it was a liter. Okay, I'm sure it's not quite a liter, but close to it. A liter is a little bit more than a quart, and that's not quite a quart, is it? Okay, but it's pretty close. So if that was a liter and that was full of water, that would be 1 kilogram of water. Okay, that's the point. Okay, so rather than talk about 1,500 liters per minute, we can talk about 1,500 kilograms per minute. Okay, now I know what this is. This is a mass per unit time. But my time is now in minutes. What time do we usually use? What's our usual unit for measuring time? We've been using it most of the day today. Seconds. So we need to get that 1,500 kilograms per minute into 1,500 kilograms, or so many kilograms per second. So I'm going to take this thing that I just wrote out of the way here, and I'm going to do a conversion here. The conversion is going to be a blank blank. It's always a blank blank. Maybe more than one blank blank, but it's always a blank blank. Equal to blank kilogram per second. Okay? So obviously, what unit are we converting here? Kilogram stays the same. What unit are we converting? From what to what? From minute to second. So our two units here, always put the units in their place. One of them's minutes and one of them's second. Which one goes where? Say again? One goes in the denominator, one in the numerator. What goes where? Between minutes and seconds. If you put minutes in the denominator, then you have per minute squared. I'm not even sure what a square minute is. Put seconds down here and minutes up here. And look what happens. The minutes cancel out, you lose those, and you have seconds in the denominator right where you want them. Right? Okay? Now we have to figure out the numbers. That's what the first line's for. How many seconds in a minute or minutes in a second? Say again? Someone said something? 60 what? 60 seconds is 1 minute. Now we got it. Now I'm going to make this a little easier on myself. I'm going to divide out a 0 here and a 0 there. Now I need 6 into 15. That will do 2 times with 3 left over. That looks like 25 kilograms per second. But because it's 3 standard digits, I think it'll be 25.0 kilograms per second. That's going to be our mass per unit time. Mass per unit time. Okay. Now, what are we missing? In order to get power, what do we need? You've answered this question several times tonight, very nicely too. Say again? In order to get power, that's what we're looking for. What is the formula for power? Force times displacement divided by time. But we don't have a force, do we? How is force related to mass? There it is, mass times acceleration due to gravity. So if you multiply this by g, you're going to have a force there, aren't you? Force per unit time. Well, what is g? This is 25.0
9.80.
kilograms per second times 9.80 meters per second squared. And that will give us, you can multiply that if you want, or we'll hang on to it and do it later. This gives us the force. The force would be with you, okay, whatever, okay. Forced you to wait, okay? That's force per unit time, by the way. Force per unit time. That's what that gives you because you got it per second. Well, there's force per unit time right there. Force per unit time, that is 25.0 kilogram per second times 9.80 meters per second squared times your displacement. And your displacement was, can I go on and erase this because I got it in the way here. Probably should have done this later. I hope I got it all down there. Okay. And your displacement is 45 meters. 45.0 meters. Okay. I think that's going to give us everything we need, won't it? Because a kilogram meter per second squared is a what? Kilogram meter per second squared. That's not a watt. That's a kilogram meter per second squared is a force. That's where we got it from. Force, right? Force times displacement. This will be a Newton. It is a force, but it's measured in newtons. Newton meter per second. That's a watt. Okay? So let's get it what it is. Okay? Multiply those together. 25 times 9.8 times 45. 25 times 9.8 times 45. Anybody? 25 times 9.8 times 45. Is that a little louder?
11,000.
Did you say 11,000? I can't hear well.
Yeah.
Okay, 11,000.
11025.
Second?
11025.
11025? 110.25?
11,025.
Oh, okay, wait. Okay, I got it. You were repeating some of it. Okay. Okay. 11025. Is that what you said?
11,025.
11025. And that will be in Newton meters per second. Newton meter per second. And what's that? That's a joule per second. And what's that? A watt. Okay. So that would be 11,225 watts. Okay. First, let's take care of significant digits. Okay. How many do we have? 3. 1, 2, 3. Look to the right. Okay, so that'd be 11,000 watts. But the original problem said in kilowatts. What power in kilowatts? So we need to change that to kilowatts. What would that be? 11.0. You're absolutely right. Kilowatts. We need 3 significant digits, so we need that 0.0 there. 11.0 kilowatts, and that's what the book has. Good for them. They got it right too. Okay? Any questions? That was a little tougher because they gave it to you in liters per minute, which you needed to get using this down here, mass per second, kilogram per second, We did our conversion, got it there, and then multiplied that by g, and that gave us force per second. Mass times acceleration due to gravity is force. So, do either 1 or 3 or both. Okay? Do any of the odds, wow, I have a whole bunch of them, 5 through 23, or 5 through 25. You choose how many you need to do so you feel good and comfortable with those. Do some of every kind, when you're looking for power, looking for time, looking for mass, looking for whatever, okay? So do several of those. All right. Now we're getting ready to move into energy, okay? Do we have the energy to do so? No. Oh, sure we do. All right. All right. All right. Now, this is exciting stuff, isn't it? Yeah. Okay. Oh, yeah. All right. What is energy? Energy really is one of the toughest things to define. Okay? Energy is defined as the ability to do work. That's why I asked if you had the energy. Do you have the ability to do the work? Sure you do. We're tough. Okay.
Try again Monday.
What's that? Okay. There are many forms of energy. This is what makes energy so tough. There are so many different types of energy. We're going to talk about several. One of these, in fact, I'll write it down now, is going to be potential energy. Potential energy is stored energy in a body. And mostly stored due to its internal characteristics or its position. Due to position. Okay? Let me give you an example of that one. Oh, man. I've been sitting too long. Okay. Trish, right? Okay, I'm going to borrow Trish's foot for a minute. Is that okay? Okay. Now, if I were to drop this book on Trish's foot, I'm not. Okay. If I were from here, it's probably going to hurt a little longer. It won't be too awfully bad because the position of the book isn't very far above her foot. What if I move the book up to here and drop it on my foot? She's not playing this anymore. Okay? That would hurt a lot worse. Why? Because I added energy to the book by lifting it. I did work on the book, adding energy to it. Now it has the potential to do more work on her foot than it did when it was down here. That's potential energy. The energy associated with the position of the book. Okay? Now that's just one. There's other kinds of... I just lost my place. I got it back. I got it. You good. Okay. There's other kinds of potential energy. For instance, those little green leaves out there, they are taking carbon dioxide out of the air, water out of the ground when they ever get any rain. I thought it was going to rain today. It was thundering like crazy, but it hasn't yet, has it? But anyway, and they are taking that carbon dioxide and water and forming simple sugars, which we can eat if we ate holly, but we don't, okay? Or the animals can eat the grass, and then we eat the meat from the animals, and we get energy from them. So that's potential energy. That's called chemical potential energy, and that's the energy they were talking about here that they said was due to its internal characteristics. So there's chemical potential energy. There's also position potential energy. That's called gravitational potential energy. You have spring potential energy. If I were to compress a spring here, it's pushing back, I release it, it hits a pinball machine or something like that. Okay, that's potential energy. Okay, all kinds of potential energies. Okay? There's one more, plenty more, but another is kinetic energy. Now, have we seen that word kinetic before? What does that mean before? Do you remember? Say again? Okay, you're really close to it. Kinetic energy, we had it in friction, remember? We had static friction and kinetic friction. Kinetic energy was when kinetic friction was when the object was moving. This is when the object is moving. So kinetic energy is the energy due to the mass and velocity of the moving object. Energy, I can't spell, due to mass and velocity of a moving body. Okay. My screen's about to lie down on me. Okay. It's losing energy. Okay. Now, there's all sorts of kinds of different potential energy. Okay. Oh, we got time. One is internal potential energy. Okay. Internal potential energy is determined by the nature and condition of the substance. For instance, another form, if you had enough of those plants out there combining and making carbohydrates, and then they get buried deeper and deeper and deeper, and bacteria work on them and stuff like this, and finally they become oil. Okay, like millions, thousands of years later, lots of temperature, lots of pressure, it becomes petroleum. Then we refine the petroleum and put it in our car, and now we take that energy stored in the molecules and move the car. So now we have, that's chemical potential energy, internal potential energy. You got lots of different kinds of energy. The one we were talking about with Trish's foot, that was called gravitational potential energy, because that had to do with how high you were in a gravitational field. So that's gravitational potential energy. Now, I like to call it GPE, gravitational potential energy. This book calls it, for short, just calls it E sub P. Energy due to potential energy, where it says E sub P is potential energy, but it's talking about gravitational potential energy. So since gravity is involved, it's mgh. The gravitational, that's because of gravitational potential energy, mass, and h is the height that it's been lifted. Like when I lifted the book from here to here, whatever that height was, that's how much more energy the book had when it was up here than when it was down there. That's the energy I added to it. Okay? Now, I guess we're going to have to stop there before we get to example 1. So we don't have any new exercises in this section, but you got plenty to work on. And you got your test, so I hope that's going well. Practice on the problems here, and we'll pick up again next week with right where we are. Good deal. Through. Thank you. Yes, ma'am.
So, I have to have surgery.
You have what?
I have to have surgery.
Oh, I'm sorry.
It's okay. So, and I have a consultation tomorrow, and I don't know if it's going to be this Friday
Right.
or next Friday.
Right.
So, can I, give my test to Gracie and she turn it in?
Yeah,
or do I
that'll
need
be
to,
fine.
fax it to you?
No. Yeah, that'll be perfectly
Okay.
fine.
Thank you.
All right. I hope it goes well.
I have 2 questions.
Yeah.
When you're doing a problem and looking at the significant numbers,
Right.
like one number is 4 numbers and the other one is 3 numbers.
Right.
How do I know how many?
The least.
The least. All right, my next question. If it's like 0 point something, do that 0 count as a
No.
significant number? So everything after the decimal?
It depends. Okay.
Well, it's like 0 point something.
Okay. 0.135. That would be 3 significant digits.
Okay, so the 0 don't count in that case.
No, it doesn't. Okay. That's just a
But
placeholder.
if anything over 0, it
Okay.
counts.
If that would have been 0.135, that would be 5 significant digits.
Okay, I got you.
Okay. Now, but how about this one? 0.0135.
You stop at 0, 1, 3.
No. Leading zeros don't count. That would still be 3 significant digits.
Okay.
Yeah.
Thank you.
All right. Glad to. Good question.